Hello, everybody. Thanks for joining. We will start in a couple of minutes, just sorting out some audio issues. Thank you.
Thanks, Gazelle. Hello, everyone. I seem to be having a technical, challenges morning. Thank you for joining our second webinar presented by Pembina Institute's Buildings and Urban Solutions program. Pembina is a national nonprofit clean energy think tank with offices across Canada. I'm speaking today from Vancouver, the traditional lands of the Musqueam, Squamish, and Tsleil-Waututh Nations. We work on policy in the areas of renewable energy, the clean economy, oil and gas, transportation, and of course, buildings. Before we start, I'd like to thank our funding partners, Natural Resources Canada, CMHC, and FCM, the Federation of Canadian Municipalities, as well as our supporting partners, Real Estate Foundation of BC, Sitka Foundation, and North Family Foundation. My name is Betsy Agar. I am a senior analyst at Pembina, and I have the pleasure of moderating this session. I'm also joined today by my colleagues, Stephen Hoy and Gazelle Ibrahimi, who are helping ensure today's webinar is a success. Stephen is producing this series and leads our communications. Gazelle is also a senior analyst in our team, and today she'll be helping facilitate the Q&A. Today's agenda is pretty straightforward. I'll start by introducing our retrofit project and then each of today's speakers. We will quickly move into presentations and follow them up by the Q&A session. Finally, I'll leave you with information about an upcoming demonstration project opportunity. Just a bit of housekeeping. I want to remind you that this webinar is being recorded and it'll be published online, which we invite you to share with your networks. To ensure high sound quality, all participants will be muted throughout the webinar. So please, if you have questions, please type them into the questions box on the GoToWebinar panel, and we'll try to answer as many as possible during the Q&A after all of the presentations are completed. With that, I'm pleased to introduce you to Pembina's Reframed initiative. Through Reframed, we are working with designers, builders, owners, financiers, and policymakers to scale up deep retrofits. We believe that by bringing all of the players together to accelerate and improve retrofits, we can address our housing crunch and the climate emergency at the same time. Deep retrofits include more than just energy savings. They lead to healthy spaces, they are resilient and protect their occupants in extreme weather and seismic events, and they are low carbon. And in scaling up retrofits, we also know that we have to keep these goals in sight. We need to keep rent affordable. We need to minimize tenant disruption, particularly in cities like Vancouver, where the vacancy rate is less than 1%. And we need to make sure that the energy efficiency investments made are returned to return the value to the building owners and the investors. Hopefully you had a chance to read our primer on heat pumps. If you haven't, you can find it in the handouts section of the GoToWebinar panel, and it will be posted alongside the recording of today's session. This primer is by no means comprehensive, but introduces the concepts, advantages, and challenges of integrating heat pumps into deep retrofits of existing buildings, hopefully kickstarting further discussions. So without further ado, it's my pleasure to introduce our speakers, starting with Jordan Fisher, who's president of Fresco Building Efficiency. Jordan has extensive energy efficiency experience in both new and existing buildings, ranging from single-family homes to high-rise, multifamily, and commercial properties. He has 14 years experience working on heat pump projects, including both air source and ground source systems. He led a BC-wide study on heat pump installation practices, led the development of heat pump installation quality standards for BC Hydro and Fortis BC, and was an advisor on the development of a BC heat pump best practices guide. He oversees a team of professionals that is actively involved in heat pump retrofit projects in multifamily buildings, including space heating, domestic hot water, and ventilation applications. Following Jordan, we will hear from Jay Jagpal, who's a principal and sales engineer at Olympic International. Jay joined Olympic in 2010 and has been actively involved in commercial, institutional, residential, and retrofits. where his strong focus on engineering sales has led to a wide portfolio of successful projects. He takes a solutions-oriented approach and is committed to the education and development of both employees and customers. His leadership in emergent projects shows up in cutting-edge engineering and laboratory buildings, residential developments, low-carbon schools, retrofitting existing institutional buildings, and zero-carbon facilities. He has a bachelor's in applied science from UBC, a mechanical engineering diploma from BCIT, and is past president of the local Reframed chapter. And finally, we have an Alterna mechanical duo, Don Curry and Thomas Barr. Don is a managing partner at Alterna and is described as a hands-on business professional with many specialties and background expertise in residential and commercial mechanical systems and process development. By gaining significant experience working at the forefront of high-performance mechanical systems technologies with low-energy building applications, he feels he has a unique perspective that helps to push innovation within the industry. He's developed an individualistic approach to developing, designing, and installing specialty cold climate HVAC systems within homes and businesses. I should note that Don and Thomas join us from Alberta. And Thomas, as Alterna's Chief Innovation Officer, he is passionate about change and throughout his career has endeavored to make a positive impact on reducing the amount of energy buildings and communities require for a resilient future. Thomas discovered a strong personal interest in improving the overall functionality and efficiency of mechanical and electrical systems for buildings and communities. Through his endeavors, he has gained experience in energy modeling, geo-exchange, solar thermal, photovoltaic, and waste heat recovery systems, and learned to construct them successfully. He has come to manage full mechanical and electrical systems from concept to construction and through to project completion successfully and under many contract formats. Okay, welcome all, and Jordan, can you kick us off?
I think you need to give me screen control. Can you see my screen now?
It's blank.
Worked in testing. Hopefully it's just a short delay. So I'll get started. Hopefully the screen comes up in a moment. So thanks for having me here today, Jordan Fisher from Fresco. I've been fortunate enough to have a chance to work on a variety of different energy efficiency projects, including quite a few different heat pump projects across a variety of different types of buildings. What we're going to talk about today primarily is air source heat pumps. We'll touch, or we'll kind of refer at least to ground source heat pumps and gas-driven heat pumps or other types of heat pumps that we also see out there in the marketplace and that we've also had a chance to be involved in. But today's presentation really is going to be focused on air source heat pumps, which are a really common technology and available in a wide variety of applications and a wide variety of climates. I'm sorry, it looks like, is my screen still blank? I guess Betsy's muted now.
Yeah.
Hopefully, maybe Stephen, maybe you can pull up the backup slides. So why heat pumps? So there's a variety of motivations for using heat pumps. A lot of these are environmental, especially as they relate to greenhouse gas emissions reductions. But increasingly, we're really encouraging people to look at heat pumps also from a health and safety and comfort perspective. For example, the ability of heat pumps to introduce cooling into buildings is something that isn't just about comfort or a luxury, but really can help address health issues, particularly with vulnerable populations in places where there's a lot of issues with overheating. There's also a lot of issues around costs with heat pumps, and heat pumps have definitely in some cases an opportunity to help reduce building operating costs. In other cases, we do see a lot of challenges with heat pumps in being able to successfully reduce operating costs, mostly as a result of the fact that there's usually a very large differential in most markets between the price of electricity and the price of natural gas, and it can in some circumstances be really challenging to overcome that gap. Certainly, we think a lot of the interest that we see right now from our clients around heat pumps really relates to environmental issues, and particularly as it relates to GHG reductions. So I think we have a pretty sophisticated audience. I'm not going to get into a lot of technical depth, but at a high level, we really just want to distinguish heat pumps from traditional heating technology, where heat is basically generated from burning some kinds of fuel at some efficiency that's less than 100%, compared with heat pumps, where we're really using a technology that's basically moving heat from one location to another, and therefore the actual operating efficiency is well over 100%, and in some cases could even be several 100%. We're speaking today primarily about multifamily buildings, and we've worked on tens of thousands of units worth of multifamily buildings, including new construction and existing buildings. There's obviously a lot of variation, but for the purposes of this presentation, I'm trying to break those down into 4 categories. So the first would be townhouses, basically ground-oriented multifamily buildings, which typically are pretty similar to residential or single-family buildings in terms of how they function. Often they may have electric baseboard heating. Sometimes they may have gas furnaces. In older apartment style buildings, those could be high or low rise. Mostly here we're talking about buildings built between the 1950s and the 1980s. And typically the majority of those are rental, although there may be some condominiums in that era as well. And a lot of that relates to sort of tax and regulatory structures at that time. Typically, these are relatively inefficient buildings. They tend to have relatively poor thermal performance of their building enclosures. They often don't have heated ventilation systems, and very often are characterized with high temperature gas-fired hydronic heating systems, often with very old, inefficient boilers, some of which have been upgraded to new, higher efficient systems. And then most of them tend to have central gas-fired domestic hot water systems. For the most part, inefficient, although definitely we are seeing a lot of people upgrade those and taking advantage of utility rebate programs to do so. And then newer apartment style buildings, again, high or low rise. Typically here we're talking about buildings built from the 90s onwards, at a time when the market had really shifted more towards condominiums. There's a mix of heating types. We do quite often see so-called electrically heated buildings, but even in these electrically heated buildings, a lot of the heat of that building is actually being provided by natural gas through things like gas makeup air units, and in some cases gas fireplaces. And then high performance buildings. And I think here we're mostly talking about new construction of relatively recent buildings. However, there certainly are opportunities for retrofitting buildings down to high performance. And we're fortunate today to get a presentation a little bit later on the Sundance project, which is taking that approach. Typically these are buildings that are characterized with really good enclosures, with very high thermal value wall systems, virtually no thermal bridging, airtight envelopes, and heat recovery for ventilation. Typically these buildings have really, really small heat loads. And I think we used to see sort of in the early days of Passive House, a lot of people perceiving these kinds of high performance buildings as sort of, you build a great building enclosure and then you sort of don't have to worry about mechanical systems. And increasingly, I think we're seeing people start to realize that while it is definitely a great way in the direction we want to see buildings going, both new and existing, to these high performance enclosures, really we really do need to pay attention to our mechanical systems in these buildings, and they can actually end up with quite a lot of needs in terms of cooling. And as an example, and heat pumps can be one strategy for meeting those needs. So in the townhouse example, really mostly when we use heat pumps in this context, we're looking at residential style equipment. So for example, in the heating system, we'd be looking at, a residential ductless, central, or mini ducted heating system. And then on the hot water, we can see a mix of either residential style heat pumps. The example shown in this picture, I think, is a Sundance system with an outdoor unit that basically makes the hot water and an indoor storage tank. There are other examples, and I think Sundance will give one later, of an integrated tank type heat pump system. So really, we're dealing, especially on the space heating side in townhouses, typically with a lot of very well-proven, well-established technology, similar to what you see in the single-family market. And what we really want to emphasize is the importance of good quality equipment, good design, and good installation practices. As Betsy mentioned, we were involved in a large study, and we've been looking at a lot of actual installations. And we have seen a lot of issues with the installation quality of these heat pumps and incorrect specifications, particularly around central and mini ducted systems, as well as a lot of issues with ducting design and installation. So I really encourage people to check out things like the Best Practices Guide put out by Home Performance Stakeholder Council and the Program Registered Contractor Standards put out by BC Hydro and Fortis. And I think we can get you some links to those after the presentation. Moving to the older style apartments, this is probably the most challenging, but in some ways the most important sector to address. As I mentioned, typically these buildings are quite inefficient and have high greenhouse gas emissions. And as they typically or very commonly have very high temperature hydronic heating systems, it's an application that in some ways isn't really ideal for heat pumps. But we've nonetheless looked at the potential for using heat pumps in these applications. We just finished a study looking at the potential to do that in a building in Vancouver. And we found that we could get about a 65 to 85% greenhouse gas reduction by fuel switching most of the load to heat pumps, but still retaining natural gas for use in peaking and backup. So it is definitely possible. It's quite expensive, and there are still a lot of challenges in overcoming that cost differential between gas and electricity. When doing that, there's a lot of challenges that need to be addressed, like siting of equipment, structural issues if you're going to be putting equipment on the roof. But we think in a lot of situations, those are definitely solvable issues with good planning and good integration. And the one thing I really want to emphasize, and I think Betsy touched on it in the beginning, while we're talking about heat pumps here, we really want to not lose sight of the importance of really trying to take a whole building integrated approach to deep retrofits, where we really consider building enclosures as well as mechanical systems in tandem. And certainly as we improve building enclosures, it becomes easier to meet those loads with heat pumps. And then on the hot water side, we have an example here, a project that we're working on. On the top left, you see sort of a common low efficiency gas-fired hot water system. And on the top right, an example of a central domestic hot water system. There are some potentials to also decentralize both the heating and the hot water. There's some advantages and disadvantages in doing that, but in some cases, it can be a good approach. But certainly on the large central heat pump hot water side, it is entirely doable. We're in the middle of doing one right now. But again, it can be challenging to make it cost effective in some circumstances. Moving to the newer multifamily apartment style buildings. As I mentioned, even for the buildings that are electrically heated, a lot of the gas use, or a lot of heat in this building comes from gas-fired makeup air. And it's absolutely possible to fuel switch those makeup air systems to heat pumps. And we're involved in a couple of projects right now doing that, both fully electric systems as well as hybrid systems that retain natural gas for peaking and backup. And then a lot of the issues we look at there, some of it, again, looking at structural, but largely we're really looking there at the electrical capacity of the building and how easy or difficult it is to upgrade that capacity to accommodate a heat pump. Hot water issues I kind of touched on in the previous section, but one thing I want to note is the potential for space heating in these buildings is the opportunity to use a different kind of form factor of heat pump. And you see in the bottom right there, there's an example of a unit, so it's, I think, in Innova 2.0, and I think Jay later is going to show an example of another similar form factor unit, and it's great to see more product becoming available. But this is a unit where there really is no outdoor unit. The actual heat pump is integrated into the indoor unit, and then it actually pulls air from the outside and expels air back to the outside through a very, very short sort of ducting run that's just the thickness of the wall. So that's a really interesting form factor and giving us a new approach to being able to integrate heat pumps into space heating in these buildings. And then moving on to high performance. I'm not going to spend much time on this. This is a picture of this building you see here is an example of a project I worked on in Vancouver. We're really just trying to show there the thickness of the envelope, or enclosure rather, made construction. And again, we've sort of touched on a variety of solutions that I think all potentially can apply to this building type. One of the interesting challenges you see is that because these buildings have such great envelopes or such great enclosures and such small heat loads. One of the challenges we find, especially in moving to a suite by suite approach to heating, which is an approach that we like, is that it's actually challenging to find equipment that's small enough to meet these tiny little heat loads. So if there's any equipment manufacturers out there listening, I'd really love it if you could help us get some smaller equipment available on the market. Moving to kind of big picture, sort of common issues we see across heat pump projects that we work on. One of them is sizing, as I sort of just touched on. Sometimes the equipment that we would like, what's available is either too big or too small, and thankfully there is more product coming on the market now. Probably the number one issue really is the cost of gas versus electricity, and it's different depending on your market and your rate class. But generally speaking, electricity is quite a bit more expensive than natural gas, and it can be challenging for heat pumps, even with very high efficiency, to overcome that gap. Certainly there's incentives available in some markets to help overcome that. And in some cases, they are able to help us overcome the cost issue. But in many cases, we see that the incentives really are not able to overcome that cost, the cost issues that we see with heat pumps. And it can be challenging to do this in a way that's economical, which is a great segue to talking about integration and whole building strategies. And again, wherever possible, we really encourage the integration of mechanical and building enclosure to really look at a whole building approach. And the better a job we do of that, I think the easier it's going to be to integrate high performance systems in general. Often we have other challenges like legal and regulatory challenges. So for example, we may have a building where the best technical solution is to retrofit to a suite by suite approach to heating. But if it's a rental apartment building, for example, it may be that the way the agreements are structured, heat's already included in the rent, and that may present a legal challenge. We will switch to the technical solution that may make the most sense. There's some decisions to be made about whether you put in a fully electric system or go to a hybrid system. And when I say hybrid, I mean with a backup with something like natural gas. And again, a lot of that's going to depend on site-specific issues that you need to evaluate. Global warming potential of the refrigerants is something I think people are looking a lot more closely at, and I think Jay is going to speak in a bit more detail. But certainly in general, we're seeing a positive trend, I think, towards moving to lower global warming potential refrigerants. And next, really sort of there's a lot of nitty-gritty issues that really come down to the success of the project. So for example, the adequacy of the electric service, or how difficult it is to upgrade, potential structural issues if you're putting equipment on roofs. Some municipalities have complicated permitting processes, and those really need to be planned out and thought through, along with logistics and site coordination. And then often, really thinking through the rate structures and thinking through things like demand charges, if you have demand charges on your rate structure, and how your heat pump's going to perform and how that's going to impact your demand. So I've had to give a bit of a brief overview, but I hope that's given you a little bit of a flavor of some of the overview of the project, and looking forward to seeing the next presentations, getting into some more specifics. Happy to answer any questions later, and then if anyone has any really technical questions, my contact information is there, and I'd be happy to follow up and have one of our design engineers chat further with you about any specific questions that you might have.
Thanks, Jordan, and glad we were finally able to align and show your slides. Somebody did just comment, Fujitsu has heads available as low as 4,000 BTUs in the J series, so maybe that points you in the right direction. Now we'll move on to Jay.
Hi, everyone. Jay Jagpal here from Olympic International. I'm going to speak to the equipment side of the conversation. So who am I? I'm a principal at the Olympic International, and focusing on engineering sales, and focus and work with 8 of the largest engineering consulting firms in the Lower Mainland. So kind of who are we? One second. Who are we at Olympic International? Well, we're the largest HVAC solutions provider for multifamily and commercial market sector in BC, and we've been around for 55 years. What do we really focus on? We focus on bringing the world's leading sustainable technologies to the BC market, and we've done that many times. And we have the technical expertise in-house to support those technologies and to put them in systems that are going to work. And over our experience, we've collaborated with many industry partners and government and policymakers to provide insight and also provide zero carbon emissions buildings that work. Our product portfolio is wide over many different spectrums of many different types of products, different systems, and it's sourced from all over the world. So, for us, we find partners that really will work with us to provide kind of cutting edge equipment that we can incorporate and support it all the way through. So, today's topic is on retrofits, and before as retrofits really start, we've got to look at what do we have to start with, and the critical information through my experience on retrofit jobs is really looking at what do we actually have to work with to start off with. And a lot of times, we'll see nameplates or serial numbers of boilers, and you can go ahead and replace those, but sometimes those are not being fully utilized, and the capacities are far more than what they require actually on site. So actual data on usage and the data on the capacities of what the devices are internal in the building are important. What's the loading of the boilers in the winter? What's the domestic hot water usage? And also, as Jordan alluded to, what's the existing site electrical infrastructure? Like how much room do they have on the panel? Do they have to pull a new feed? What voltages are we looking at? Other items are, what are some of the space and sound requirements? Where are we located? Is the property line, is outside of property line? Since we are talking a lot about air source heat pumps today. So we're going to discuss now kind of what's in the market currently. What do we have to kind of use as products today, and what we have been using on projects. That is, to start off with, is a through-the-wall, fairly simple device. So this unit sits on the inside of a room and has two small 4-inch or 6-inch ducts going out to the outside of the building, in which it brings in air for the condenser and will provide either heating or cooling to the indoor space. And this can be basically hung on a wall and ducted fairly easily on an existing building, and only needs 120 volts of power. It also has a capability of connecting to auxiliary heat and supplemental heat if you do have a condition where you're using this below 5 degrees Fahrenheit or minus 15 degrees Celsius. So it does have heat pump capability going down that far. And full CSA approval, full ETL approval, and actually stocked in North America. These are, as Jordan also mentioned, these products. We've got split systems and VRF systems available today, and these are designed for cold weather climates. They're designed specifically for the Canadian marketplace, where we can do heating continuously down to minus 13 Fahrenheit, minus 22 Fahrenheit, and have full heating all the way down. And if there is further supplemental heat needed, there are interlocks available for these. And the way these units work is they have a refrigerant line from the indoor unit to the outdoor unit, and refrigerant is the medium for heat transfer. For packaged rooftop units, we do have heat pump rooftop units, which can replace gas-fired make-up air or gas-fired rooftop units. So these units have a DX circuit within that'll make heating for the DX core or heat up the indoor air. And however, there's limitations to these heating circuits in which the air entering the unit, entering the heat pumps, can't be below 40 degrees Fahrenheit or say 5 degrees Celsius. So there's limitations in which you have to either include preheat coils or heat recovery coils on these units to go down further. So if we're looking at buildings where we want to replace the boiler and we have hot water in the building doing both the heating for domestic hot water and also for terminal devices. We do have products that can replace the boiler per se, and these products can heat down to 5 degrees Fahrenheit or minus 13 degrees Celsius. So we've used these on current jobs where we're doing the domestic hot water and the heating for the building. In cases where you want to have a separate unit doing the domestic hot water and a separate unit doing the heating for the building, we do have two products that I'm showing. One is a Now product made out of North America, which is designed to make take water from 50 degrees Fahrenheit to 160. The second is a Mayakawa product, which is out of Japan and has been proven in the Asian market that we carry. That's run with a CO2 refrigerant. And these are both specialized units designed to make domestic hot water and heat domestic hot water. Some success of bringing global products to BC now, there's a lot of solutions in Europe, there's a lot of solutions in other parts of the world that can work for us in BC, but it takes something to bring them here. So here's some examples of what we've done, some success we've had. Becca is a radiant ceiling design, radiant ceiling product that was used in the Olympic Village, Falls Creek, and it's a German product, and it's been installed in over 600 square feet of ceiling space. One is using Jaega, which is a Belgian product. It is heating and cooling terminal units, and we've used that successfully in the Vancouver House and other many projects in the Lower Mainland. And the one that I'm going to focus on today more so is AirMech, and we've got over 200 installations of this product, and it's an air source heat pump product primarily. They've got 30 years of experience building air source heat pumps in Europe and are the leaders in Europe. And also, we happen to be the biggest representative for them in North America. So what did it take for us to bring them and be successful in the BC marketplace? Well, the first thing was the partnership with the manufacturer is critical. Working through every level of certification, every level of performance, every level of integrating these on the job site with North American construction standards. It's involved innovating their existing products to fit the market conditions of BC. CSA certification, ETL, getting them certified with the AHRI electrical certification, and the key item for long-term success is really having a trained service and support team to support their product the way they want to support it. And we've had this product for 10 years now, and it's been a learning curve, but we've been committed all the way, and it really takes a partnership with the manufacturer to drive it home. So one case study and example of retrofits that we've got an example of in our market is with the City Hall. So Vancouver City Hall in 2017 did a retrofit, and they installed this NRP unit on their site, the City Hall site. This has so far saved them 45% in gas usage and 34% in greenhouse gas. And that's its first phase. It's actually another phase where they're going to use this unit and to even colder climate conditions. And we expect to see the results from that in probably the end of this year on further greenhouse gas reductions. And the one item that I want to point out by working with European manufacturers and the way products are certified in Europe is Eurovent. And the performance coming out of air source heat pump manufacturers, it needs to be looked at carefully, because the more we move into retrofits, the more we look at using air source heat pumps as a primary heating device, we need to look at the spectrum of all of its operating conditions. And a key part of the operating conditions is defrost. So in our marketplace, as soon as you go below 5 degrees Celsius or 42 degrees Fahrenheit, the unit will start going into defrost. And what happens is frost starts forming on the condenser coils. And there needs to be a way for the machine to reverse this cycle and remove that frost so it can continue providing hot water all the way down to your coldest condition in the environment, in the climate that you're looking to serve. And what Eurovent does is it actually has seen this over the years to be a very important measurement point, and ensures that every manufacturer in Europe include that defrost derate into their performance, into their heating performance. So it's upfront and included already in your COPs. It's not added on after. Because what happens is what we've seen in our experience is different manufacturers deal with defrost in different ways. And if you're using this as a primary heating device, you want to have a look at that, how that's being used, and what the performance is during the defrost conditions. So one other question we typically get on heat pumps is the life cycle of the equipment. What is the best practices for maintenance, components, and also refrigeration leakage rates. So when we look at heat pumps now, we're using them as a primary heating device. Like I said, the run hours will typically be longer than if you're using the equipment as a chiller only. So we're using scroll compressors now for the most part in a heat pump use instead of a cooling usage. And with heat pumps, now you're running this unit for longer hours. So the best practice for maintenance is actually logging the hours on these compressors and knowing what the manufacturer's recommendation is for compressor replacements. Because if you're running these compressors for longer, scheduled replacement of compressors may be needed, and that will vary based off of compressor manufacturer and their guidelines. The second, so that goes right into the replacement of components. The leakage rates on equipment depends on a few things. Depends on how well the unit was installed, especially if it's a split system or a VRF system. What was the quality and installation? Are we using the equipment on its outer limits of its performance envelope, or are we using it well within its criteria? Are we really pushing the compressors at high pressures at all the time? Or are we using it at part load conditions a lot of the times? And that will dictate how much stress we have on the components and the piping, and what the leakage rate and the impact on the leakage. And the leakage rates ties directly right into the embodied carbon conversation. And what we're seeing now is a move and a recognition of embodied carbons in heat pumps, and a move from synthetic refrigerants over to natural refrigerants. Is being headed up out of Scandinavian countries and Europe, in which we're working more towards CO2 and ammonia and propane and other natural refrigerants. At the same time, R32, R1234YF, and these other refrigerants are coming into the marketplace slowly into North America, and we're working with our manufacturers to see if we can speed that up. So please, if you have any questions, you can reach out to me, jay@olympicinternational.com. And thank you, and looking forward to the questions later today.
Thanks, Jay. That's great. It's nice to see that there's a range of products already out there, and that we're starting to see new ones come online. With that, we'll switch over to Don and Thomas, and I think they'll address some of the cold climate questions that are coming in here. So take it away, Don and Thomas.
Thank you for the introduction, and hopefully we can meet to the same standards that our previous presenters have had. So thank you and welcome, everyone. Hope you're all doing well. My name is Thomas, and Don and I will be speaking to you about heat pumps and deep energy retrofits, a contractor's perspective. We're going to basically, our backgrounds are pretty extensive in high performance buildings. We've done a lot of conventional and a lot of net zero or passive house style projects. We've done a lot of Alberta's first, such as the first commercial net zero building, the Mosaic Center. We've done the first net zero affordable housing project. We've done the first net zero church, as well as worked on the first net zero or passive house town hall in Valley View. And today we get to have the privilege of discussing to you a new project that we've been invited to work on within Sundance Co-op in Edmonton, Alberta, which will be Canada's largest retrofit project to date. Second. So in our presentation today, we're going to discuss basically 3 key topics as related to this project, as well as other projects. We're going to talk about process versus technology. We're going to talk about the process that we have undertaken on this project, the conventional versus the integrated approach. And then we're going to also discuss some of the lessons learned on the Sundance project. Again, this presentation will be focusing more on the mechanical and energy side of things, as there's been a previous presentation done on the building envelope and upgrades, and I'm sure that Betsy would be happy to share that presentation, and we'd be able to field some questions offline on to the rest of that, such as the building envelope. So Don?
Great, yeah, thanks, Tom. So looking at kind of looking back on previous larger efficiency upgrade projects, looking at the process of, how we adhered to sort of an outdated process, I would call it, to be quite blunt, where inputs such as, load analysis and design work and budget allocation, they've all been sort of been collected in separate silos, and these overall efficiency upgrades, they're not quite viewed as a whole before the actual construction commences. So what we're trying, looking at this, a little deeper, you find that sort of this pre-design energy modeling is not realistic in essence. And, there's minimal discussion between project coordinators such as designers and contractors. And, these inputs remain siloed, and eventually so do the outcomes, right? So, looking more to the future, we're trying to focus our attention more on an integrated approach to this project development. And, we want to use these efficiency upgrades and approach them with a larger picture in mind. And then all of these inputs can be coordinated more naturally and aligned to form more of a common project outcome. So with this, it would hopefully intended to lead to a much more comfortable building, a healthier indoor environment, and healthier occupants based on those 2 things. And then of course, reduced overall operational costs, and then a overall carbon impact with greenhouse gas emissions. So, we like to say in the office, like the intent, we like to say that if efficacy is sort of the outcome. So it's about efficacy, not just efficiency, where better technology doesn't necessarily breed better overall outcomes. So, yeah. On to you, Thomas.
And so some of the conventional project deliveries is very linear. You have an owner, you have a consultant that's your lead, and they manage all the other sub-consultants. Then you have, again, a general contractor who then manages all of these separate trades. And so this conventional format is very linear and doesn't encompass this integrated project approach. And so again, the process flow usually comes again from a very linear approach. It's an idea to feasibility, to a design, to construction, commissioning, and turnover. And our experiences from this conventional approach, there's usually a lot of gaps. And so what we've been trying to do and have been doing successfully with a lot of our project partners, such as Butterwick Construction, who we worked with on the Sundance project, we kind of look at it from a more holistic approach, right? Where it's more of everyone sits down at the beginning. We have the owner, all the construction management teams, the interior designers, mechanical, electrical, millwork partners, and everyone, where they're focused on the project outcome. Because when you look at these deep energy retrofits, it's not just about technology, it's about the process, and the process is equally important. And a lot of these types of projects tend to be a lot unfamiliar, and the solutions are complex, and they really there are typically more than one type of outcome. Scopes and deliverables overlap between various types of trade partners, and we need to make sure that there is no missing gaps as well. And so our collectivism on the Sundance project has allowed us for an integrated approach where we have had many hurdles to overcome within this integrated approach. And because of the integrated approach, we are able to be more successful. And so the project overall started with energy modeling and optimization. This is where we kind of evaluated what are the best technologies and how could we best apply them. we focused in on the design and planning so that we had an efficient, construction and execution plan. And, that we made sure that the commissioning and the measurement and verification of the systems that we modeled were going to be, we'd meet those targets. And so this whole process flow doesn't just become a project, but becomes an ongoing system that allows the building owners, the tenants, and the to understand how and where they're utilizing their energy the most effectively and most efficiently, so that they can either adjust the behaviors or the physical components thereafter, whether it be controls or operation.
Right. So a little background here on the Sundance project here and how it sort of came to fruition. First of all, it's super exciting and we're really happy to be a part of it. So the opportunity arose it was early 2018 to submit a proposal under NRCan's Green Infrastructure Phase 2, Energy Efficient Building Research, Development and Demonstration Program. It's a mouthful. So Sundance Co-op members collaborated with Butterwick Projects, whom we were hired under, to submit an application. And in early 2019, Sundance received the confirmation that they would receive a contribution from NRCan for this large-scale retrofit.
And so the project overall, the delivery was very important in the beginning. In the beginning, we worked on a digital capture, did the energy modeling and design, made sure that we understood how this building was going to be done. So there's three major components to this system. There's the building envelope, there's the mechanical system, and the electrical systems. And so for us to do a deep energy retrofit in a cold climate, the best thing that we know is to, reduce the energy not needed, the negawatts before the megawatts. And so we, the primary focus was to do a panelized system on the outside of the building, where it's not just a frame or a chainsaw type of approach, as my colleague Stuart Fix likes to call it, where you're cutting down everything and you're building straight up from frame. This is where we actually measured and digitally captured the building, comprised an energy model, and then built the panels off-site. And so those panels were built in Butterwick's facility, and then they were mobilized to site, and prep work of the building was done to ensure that the application of them was done sufficient and efficiently. So then they were craned into site, and I think on the first pilot phase of this project, we did a floor per day. So it reduced our on-site demand. And it's very important for us to understand that these deep energy retrofits, especially in this particular project, the occupants were still there. The tenants were still living in their homes. So we had to be very mindful and respectful of the conditions that we had. And so this is kind of what the finished product looked like after we had panelized it. And it was very efficient and very productive.
Yeah, so I would say on our path to a good energy system design, we like to define three sort of critical components. And in regards to Sundance project, we find our source as source energy as our passive solar, our internal gains, and our electricity. So to harness that, we look then onto our load, I should say, which is our current demand. And in this instance, this has been reduced significantly by adding exterior panels, right? Sort of the old the energy sprawl concept, where this will most definitely increase its thermal resistance to outdoor weather conditions, right, and improve natural air infiltration, and overall building a tighter envelope and ensuring minimal thermal bridging, while paying close attention to the building details such as corners, windows, doors. Yeah, and then on lastly, but not least important, is the distribution system, which basically comprised in this instance of an electric air source heat pump with an outdoor unit, which contains a compressor. Obviously now it could be considered a condenser or an evaporator, depending on what cycle it's in, and a vertical indoor air handling unit, which uses refrigerant as a means of energy exchange, whether heat or cooling. In addition, we're using the existing ductwork systems with modified plenums and sort of updating the control systems. And looking at the HRV. So as we build these tighter buildings, you need better ventilation. So the HRV is much more of greater importance. So we went with a partially ducted distribution system to serve the exhaust and bathrooms and the kitchen area, while supplying fresh air to the indoor air handler, the common return air plenum.
And so overall, the source, the load, and this distribution, we have many choices in the modeling stage and in the design stage. And we as a collective and as a project, we are very technology agnostic. And so we're not going to basically pigeonhole ourselves to one different types of technology, but we're going to find out what's going to be the most economical and most viable solution moving forward, which gives us the overall solution.
Yeah, no, good point, Tom. So looking a little closer at the specifics of these mechanical components, you know, for space conditioning at the top there, we chose the Daikin Sky Air system. I think it was about a 24,000 BTU capacity. The indoor unit was vertically positioned, and then it was served by one outdoor side discharge heat pump using single phase power. Fresh air ventilation, again, we used an HRV, which is the Vanny G2400, which has a high efficiency polypropylene core, quite a robust unit. And then the domestic hot water, we went with the Ream 50-gallon hybrid electric air source heat pump hot water tank, which we've had a lot of success with in the past. So looking back, lessons learned over this project, you know, there's lots of lessons. We'll just kind of keep with the more important ones. Now, the pronounced design considerations that came up, you know, was whether to go with a single outdoor unit per dwelling or a single outdoor unit for multiple dwellings, and zoning the indoor units respectively. So the complexity of this decision cannot be overstated. So we spent a lot of time looking at this and going through budget iterations and whatnot. Other important considerations made during this stage was the outdoor unit location and selection. You know, the tenant and owner preferences were very important, where, you know, potential noise had to be considered, as well as architectural aesthetics, you know, which include ideal use of space, you know, next to sidewalks, backyards, and decks. You know, these are people, they're living there, and they don't really want to see these things and be too pronounced by them. So we also must have to take into account the legal boundaries and property lines, and the access and egress, and maintaining a, you know, a proper emergency evacuation plan route. Additional considerations from a contractor's point of view would also be the water and the ice buildup and how to mitigate this under these heat pumps, because this is often overlooked. Serviceability to the outdoor unit, do we have it? Line set installation details, you know, will trenching be needed? Will frost protection be needed, and how much in this trenching? Considering, you know, once the line sets are buried, this leaves leak repair next to impossible. We also must take into account, you know, overhead eaves leading to unwanted elements such as rain, undermining, you know, the unit operation. And very important, you know, is the clearances to the building to the heat pump. You know, since proper operation airflow must be maintained, you know, any flow restrictions will hinder overall capacity. You know, and lastly, electrical and line set penetrations compromising building envelope have to be carefully planned. So those are some of the more important ones. So yeah, what happens when you don't read installation manuals or take into consideration of the cold weather issues for heat pumps in Alberta? Well, this. Boom. Yeah, this is all too typical of just not reading manuals. And, you know, we like to see 36 inches minimal to allow for ice buildup due to, like Jay said, you know, the defrost cycle after the water is shed off the heat pump coil. You know, you have to make room for that. Otherwise, you're just going to have a huge block of ice just like that.
So another thing that we had to start learning about was the indoor equipment placement, as this was an existing building and they had a gas-fired furnace, gas-fired hot water tank, no fresh air ventilation, no HRV, and their standard exhaust systems were just bathroom exhaust fans with a kitchen exhaust fan. So we had to be very careful and cognizant of the existing space that we had, and would that actually work with the new equipment. So should the air handling unit be vertical or horizontal? You know, where's the location of the HRV going to be? The location of the hot water tank? Some of the limitations in the existing mechanical room. Do we have enough space for all of it? You know, services, are they all available? Do we have all the proper drainage requirements for the new equipment? You know, these indoor units are going to require a condensate line. for the cooling season? Do we have all the electrical connections available? How far is it? Do we have even available electrical power capacity? And then also looking at the control connections. What are the existing thermostats look like? Can we piggyback off the existing wiring, or do we have to look at new styles of wiring or new ways of doing that? There's also architectural considerations. Serviceability is a very important one. Do we have enough room to service the unit? As Don indicated, we need 36 inches below the unit outside and proper air throughout. We also need to make sure that we have proper access around the unit so that, if we had to replace any components, we could do so. Do you also have sufficient air clearance for access from the electrical panel? And so in a lot of these tight mechanical rooms, they try to put in the electrical panel, and there's a lot of new codes that we have to take into consideration. This building was originally built in 1978, and unfortunately, the code is completely different now. And so when we open up the walls, we have to be cognizant that anything we change meets today's standards. Don? Don, did we lose you? All right. So the next other important lessons learned that we've come from this is that the interior installations are occurring while occupants still occupy the space. This makes for difficult coordination efforts, and therefore planning is all the more important to reduce the impact to the occupants. And so we have a few major components that we have to consider and that we are working around. So air handling unit, the space conditioning. What are the existing duct sizes and limitations? The existing ductwork was used by a high temperature gas fired unit where it was delivering higher heat with lower volumes, where we're now delivering lower temps with higher volumes utilizing an air source heat pump. Granted, we did lower our load on the building, so this should balance out, but considerations must be made and confirmed. Also, the location of the drain for the condensate line are essential to ensure no water damage occurs during cooling mode. We also have to be cognizant of the balancing, the low static versus high static air discharge, adding duct that was not needed or that is needed, and also considering the existing plenum size. So what kind of modifications need to be done to the existing duct distribution system to compensate for the new types of equipment? So,
sorry, I just got connected again. Keep going, Tom.
All right, thank you, Don. And then the installation of the line set from interior unit to the air handler. This is, again, very important to the penetrations. We have to run in rim joists where possible to reduce impact of the interior finishing. And so again, that is a new component that wouldn't have been there before. Controls, again, possible to piggyback off of existing thermostat wiring. And was the thermostat even located in the right place to begin with? This is actually a big comfort control issue that we see in a lot of existing buildings today. Is the thermostat in lieu of a light or of a window where the sun shines upon it and giving us false readings of the space? Is the unit on an exterior wall where it's going to be picking up the resonant heat or cooling from the outside of the building ineffectively? And again, just making sure that that is in the proper location. And with having multi spaces, we have to also see if there is the need to put in, additional remote sensors for a balancing of the temperature throughout the building. Next, we had to start looking at the HRV, the fresh air distribution. This existing building had direct vented exhaust for the washrooms. And so by utilizing an HRV, we didn't want to necessarily continue with that same adage. So we had to cap off the existing exhaust fans to the exterior, remove them, and then see if we could even utilize the existing ductwork runs so that they would have proper supply and exhaust. And through our experience, obviously we had to add a few things, and understanding what we had to add and what we had to add was sometimes difficult when all these existing components are behind the wall. So again, installation of new existing duct runs would have to be done in the joist space to minimize interior alterations required. Again, use of existing mechanical walls or voids that already exist helped us out. And, it proved to be difficult. And Don and I think everyone in the retrofit market would love to see some form of X-ray product out there that will allow us to look behind the walls and see all the components that are there. So again, my wish list is we need something that can provide us that interior wall cavity analysis without having to open up all the walls, because that adds significant costs and disruption to the client. And again, for the exterior on the HRV, we use supply and return locations on the exterior. We're, used PVC sleeves during the pre-panel installation, so that when the panels were installed, they were well sealed and well cleared. The kitchen exhaust had to be retrofitted from an existing style hood with a recirc fan and a charcoal filter. The new exhaust vent from the HRV also needed to have a grease filter as per code. Controls, the central controller for the HRV will be located in the mechanical room and possibly by the thermostat. That we will determine shortly. And then the additional installation of booster switches in the washrooms and in the kitchen are also required. So again, additional things that we have to be aware of when doing the installation of the HRV. The hot water tank, some of the considerations we had to do was, is the existing location sufficient? Would we still have access to the existing water manifolds, both the cold or the hot water and even the cold water inlet? A very important component here is because before we were using just a natural gas direct vented unit, we're now using air source heat pump, and the electrical capacity is a critical thing. The controls are integral into the unit that we selected with an easy 4-button stat, which allows us to go between efficiency mode, which is full heat pump, hybrid, which is a balance between the heat pump as well as electric elements built in. You can go straight electric, and as well as a vacation mode option. And so relatively speaking, we had to also ensure that we had enough clearance from the existing electrical panels because when it was originally built, they did not. And so we had to make some modifications to allow for that. And the last but not least is the plumbing. You know, for the new venting, as we added new panels to both the walls as well as to the roof, we had to extend all existing plumbing vents on the roof so that it can be accounted for when we did the installation, as well as making sure that they're properly sealed to ensure that we had proper sealing. And so here's some pictures of some of the preparation that we had to do for site. Where my mouse is here, you can see some of our inlet and outlet penetrations, and you can see where we had to build some additional cribbing for where the walls would sit. So one of the other major lesson learned was the electrical. So the plan was originally to abandon the natural gas lines and replace all gas-fired furnaces with air source heat pumps. So getting rid of the gas meters, you know, will on average save about $650 per year per unit, for a total of roughly $38,000 in annual savings by getting rid of all the natural gas lines. So the panels were currently 60 amps, and they would require an approximately 125 amp service to run the heat pump as well as the hot water tanks. And so major cost implications and hurdle was developed as, again, the existing transformers, pedestals, and services were insufficient to compensate for this. And so throughout this entire iterative process, we had to look at what was better, single phase versus 3-phase. 3-phase obviously gives us access to better or wider range of products from the commercial market, but also adds significant costs to the installation, as we'd need completely new pedestals, new wiring, and so on and so forth. Now, even though we still went with a single phase system, we still had to upgrade the pedestals, the transformers, as well as the lines going to each individual suite, including the panels themselves. So again, the discussion was made or had early on between single phase and 3-phase, and I think this was one of our largest hurdles on the project. As you can see in my on the drawing there, there's a lot of paths from the pedestal that we have to take into consideration. Again, more disturbance to all the tenants and the existing users. So again, we decided on the final to go with a single phase system, which meant a single indoor unit per outdoor unit, which again, for a lot of reasons we can discuss after, was the best approach for us. Don, are you there?
Right. Can you hear me now?
Yes, sir.
Okay. So yeah, going on to commissioning and the lesson learned here. Commissioning is often overlooked, I think, in general in mechanical systems. So we want to ensure that our systems that we put in and carefully designed and planned, that they're going to be properly balanced and operating as efficient as possible. So with the new changes to the existing ductwork, for instance, we want to ensure that all areas are receiving proper air distribution, and that an actual balancing report is conducted and verifying that we have the right BTUs per room and whatnot. And then obviously controls, ensuring all components are operating as such based on control and call for heat, call for cool. And all the boxes are checked for things like refrigerant flow, compressor operation in summer and winter. And when we go in there and install this system in the summer, how is it going to operate in the winter? So it's kind of a twofold commissioning where you have to go back and just make sure that it is operating as intended. Thermostat function, HRV function, equally as important, like that, and the domestic hot water delivery. Is it actually performing to what we had in mind?
Perfect. And so overall, some of the lessons learned, Don and I came up with kind of a wish list of what we would like to see coming from, a collective industry approach. We think the equipment needs to be smaller, both physically and in capacity. Again, thank you for the note about the small 4,000 BTU units. Again, that's for a multi-head approach, and that becomes a bit of an issue on this project, but very useful to have. But then we also were hoping that equipment could be combined in one location. Europe has started to lead the way on a lot of different types of product development, and as Jay has kind of indicated, they've started to bring in these types of innovative equipment. Now, we were looking for hopefully to see if we can combine these systems into one, as they all kind of work synchronistically together. So heating, cooling, fresh air ventilation, and domestic hot water. Is there a way for us to develop that kind of product that would reduce the impact of the space or of the space requirements, right, as well as the potential electrical requirements? We also think that the product could be also more aesthetically pleasing. Some of this early on product is not so aesthetically pleasing, and so how can we try to find ways to architecturally integrate these systems into the building, similar to what they do in the solar industry with integrated photovoltaic systems? And project partnerships. All industry sectors must be beating the same drum. And universal design guide, a standard for deep energy retrofits. And our hope with this pilot project and the efforts of Butterwick Projects and Peter Amarongen, that the Canadian government might be able to develop from this a universal retrofit guide that would allow both all industry stakeholders, from designers to contractors to even project developers, to understand what are the implications, what are the requirements, and how can we create a best practices moving forward. Understanding that every project will be unique, we must still find a way to create some common rules for how we can do so. And to give you guys a bit of an update, with the Sundance project, we completed the pilot project on 2 units late this year, 2019, and things are now being ramped up to start working on the remaining 57 units for the installation of the panelized system, and therefore the upgrades associated with that. So another thing that Don and I kind of wanted to ensure that we have created is from that, project partnership and guide for deep energy retrofits, is also the creation of a consistent training program across all provinces. Now, we do have trades organizations that do provide skills trades that are uniform, but they're, again, working in many provinces, there are still some discrepancies between what those actually look like. So we appreciate your time today. If you have any questions, feel free to contact us directly. You can contact us via our website or through our contact information provided by the Pembina Institute.
Thanks, both. There are lots of questions actually coming in about the Sundance project. One question was, did you actually add exterior prefabricated panels to that building? Yes, we did. or they did, and we'd be pleased for you to refer to a previous webinar that we recorded with Peter Amarangan, who I believe is in attendance at today's webinar, probably sitting on his hands trying to answer questions that are rolling in. You can, if you just search for Sundance on the Pembina.org website, you can see that webinar to learn more. So before we kick into our Q&A, I want to thank our presenters for great information, a good range, and lots of questions rolling in, which we won't be able to get to, unfortunately. But we have a quick poll just to get your feedback on what you're thinking is most important benefits of retrofitting with heat pumps. We'll try to move this quickly just so that we can reserve some time for questions.
Can't vote?
We can't vote.
I know. Aw, shucks.
All right, another 15 seconds. Great. So, looks like the biggest benefit that we're feeling about heat pumps is the lower carbon pollution when powered by renewable electricity. It's a good observation. The higher energy efficiency, almost tied as adaptability to existing heat distribution systems, better indoor air quality. 1% said other. So if you want to write that in on the question line, what you're thinking is other benefits, and anything else you think that we should take note of, then please let us know in there. Great, so let's move into our Q&A. I have a question about codifying best practices. If you could each name one thing that you really would like to see incorporated into retrofit codes or best practices guides that would improve the quality of heat pump retrofits, and make it quick if you can. Go ahead, Jay.
For me, I'll start with I think really finding out what the capacities are on site and what the heating requirement really is on site, so that we don't oversize equipment and oversize heat pumps. That's my number one.
Great, Thomas.
Kind of reinforces what Jay just said. Energy awareness, and right before you ever solve a problem, you need to become aware of all those conditions, not just the capacities of the unit, but a proper energy model compared to what the actual building's performance is. And so from there, you have a good understanding of what can be done to reduce your loads or install new systems.
Nice, Jordan. We don't have sound from you, Jordan. Sorry about that.
Oh, mute.
Good. There you go. Oh, go ahead.
I would say on ducted systems, better evaluation of the ductwork. We're seeing that very common on retrofits. The ductwork's undersized, and we're not able to get enough airflow through the systems, even if the heat pump itself is theoretically able to meet the need.
A quick one from you, Don. Thank you, Jordan.
Yeah, and I would just iterate Tom's back awareness. That's a very big key component. Pre-design.
Great. So I'll just, there's so much interest in the Sundance questions. Curious about, sorry. Actually, I'm going to start with Jordan. Electricity is more expensive than natural gas, as you mentioned, and so often a deterrent for installing heat pumps. Installing a heat pump with an airtight envelope increases the thermal comfort and financial benefits, but without updating the building envelope, a building owner would reduce their GHG emissions, but would they gain any operational financial benefits? How do we overcome some of these financial barriers is the kind of more general question for existing buildings?
Yeah, so I mean, it's a great question. I think a lot of it's really site specific. So we see in some sites where we can use really good quality, especially often cold climate heat pumps that are operating at really high COPs. I think in those circumstances, sometimes we can overcome that cost differential. And then the reality is, often just the cost differential is so large, and that depends somewhat on where you are and what rate structures you're in. We see them anywhere from, let's say 3 times difference to 6 times difference. So the reality is sometimes you can't overcome those differences with current rate structures. And so I think to really overcome that, we either need a dramatic improvement in the technology, or we'd need a significant change in the rate structures. And I don't know, there's a lot of way around that. We do see some equipment in Japan that we're hoping and trying to bring to North America that has quite a bit higher COPs, and we hope that more of that technology will become available in North America and at a good price point over time.
Yeah, great. And those are some of the questions that we're trying to tackle with our Reframed program project. So, everyone's heads are in the same place as show me the money and what the cost benefits are. But that leads nicely into a question for Jay. There are lots of questions about the through-wall heat pump, questions about unregulated air leakage, what's recommended for systems for single family, and comparable costs for residential through-wall systems.
Well, yeah, through the wall system it's a great product for a particular application. That's if you have the wall space for it in a unit that you can actually mount it. And there is so it comes in 2 sizes. It's either 9,000 MBH or a 1 ton, which is 12,000 MBH size, and that's cooling capacities, and the heating goes all the way down to the temperatures I mentioned in the slide in the presentation, and there's a D rate. So it's a particular application, and the cost comparable to the split systems is less. It's much less because you're not running piping, you're not having to provide power to the outside of the building. Yeah, don't have to pay for refrigerant charges and using a refrigeration mechanic. So the trade-off is that now with the split system, you can mount that indoor unit anywhere in your.
Just lost your sound, Jay.
Can you hear me now?
Yes.
Yeah, sorry. So with the split systems, you've got more options on the indoor units and the positioning of them in your suite. And sometimes the split systems, well, for the Aurora type Daikin units, they can offer more heating capacity than the through the wall units can. So those are the main differences. With the through the wall, you've got some limitations on how much heating output you can get out and what you can do with it. With the split systems, you got more options, but it's going to cost you more upfront.
Great. I'm going to ask a question about cold climate heat pumps. Curious about what the operating efficiency is in places like Edmonton. Somebody's mentioning that they live in Hope, which I don't think is quite as cold as Edmonton, but could you speak to some of the efficiency challenges in cold climates?
Yes, so the cold climate split systems, the compressors designed for these condensing units use vapor injection as part of their technology, and what that does, it increases the efficiency of the COP. So in our environment, we'll see COPs of above 2.5 when it comes down to our conditions. So what would be an air climate condition? It would still be in the 2 range. This would be over 2, where traditionally regular heat pumps would be below 2, getting close to 1. So there's still a trade-off there for that.
John, can you speak to that? Maybe is there some particular experience in Edmonton?
Yeah, no, I think he's pretty close. I don't know if you quite get to 2. Like we get -35 for sometimes a week, sometimes 2 weeks, and hovering COPs of 1.73 to 1 to 2. That's fairly realistic. And we find that actually engineering data is actually not as skewed as I thought. Like I would imagine that they kind of shoot high, right, and we go low, but that's quite the opposite. We find that they're pretty considerate with anticipated low ambient conditions.
And a quick follow-up to that, do you know what the TEDI was for the Sundance project, just to understand, what the relative air tightness and thermal targets were for the building that we're working with your heat pump design?
So did you say the TEDI?
The TEDI, and I don't know if you know the air tightness as well, but.
The air tightness, I think, was targeted to be around 0.6 to 0.8. I'd have to validate that from the actual report, and that's air changes per hour for the infiltration.
Peter's sitting on his hands right now, for sure.
Probably. I'm going to look up, if you guys don't mind, I could look up what the actually target was and what we're trying to achieve within that. Give me one moment.
Sure.
In the meantime, I can realize I didn't answer one of the questions regarding the through the wall leakage. So we've been using these through the wall units on BC housing projects and locally in BC. We've got four in construction, and the reason we're using them there is because we can actually pass the step code requirement for air leakage with these through the wall units compared to a standard kind of through the wall PTAC unit, which would have a much bigger opening. So that's the reason why these units are being a little they're used more in the marketplace right now.
So to answer that question, the original air tightness was approximately 6.5 air changes per hour, which was average, quite high. And with the reformat, it is targeting to be 0.7 air changes per hour. So right in between what I had actually indicated. And again, the upgraded insulation from basically an R20 to an R41 for the wall system. Ceiling went from an R28 to an R78. The foundation went from an R4 to an R38. No basement slab insulation because we didn't want to mash up all the concrete. That just wasn't viable. And so, yeah, those are kind of the main parameters of before and after.
Peter's no longer sitting on his hands. He said we modeled a 0.7 air change 50, and that's what we got. We hope to get better with practice, was his comment. Thanks, Peter.
Okay, good. Thanks, Peter.
It's good to have you listening. So I'll just, we do need to wrap up, which is pretty sad, but in a few words, could you just say one key idea about fuel switching for their next retrofit that you would like deep retrofit designers and building owners to take away? Jordan, kick us off.
Power equipment.
Power equipment.
Smaller equipment.
Smaller
Okay.
equipment. Pardon me. Yep. Good. Next.
I think for fuel switching, it's a matter of, again, identifying what the needs of the project are and what the best available technologies are, whether it's a combination of heat pumps or batteries or photovoltaics or building envelope. I think that, for the larger intensity buildings that require a lot of makeup air, like commercial buildings, there's going to be some significant fuel switching. For residential, I believe it could all be done electrically.
Nice. Don, I'm going to pass over you. Sorry.
That's okay. That's okay.
Jay, go ahead.
I think smaller equipment, combined equipment is what things that I'm working towards, is combining equipment and making it easier for someone to have a combined packaged approach is what I'm looking at.
Yeah, and there's some comments in here saying that there's a lack of expertise, and so as we start to introduce those more complex systems that aren't kind of a linear swap out for furnaces, then certainly it speaks to that expertise challenge. So, but now we know we have a range of expertise here available, and I'm sure you have lots of peers on this line as well who can contribute. So I want to thank you all for your presentations, and we'll wrap this up. Thanks to the audience for really great questions. Great questions rolled in even during your registration. Just want to remind you, this webinar series is part of a larger project, which will be formally launching in the next few weeks. We're kicking off with an RFP, which is scheduled for release this summer. We'll be looking for multidisciplinary teams to design deep retrofit solutions for low-rise residential buildings in the Lower Mainland or Victoria areas. Teams will be participating in a 6-month exploration lab to develop concept designs with support from climate, energy, and health experts. If you want to learn more or intend to answer the RFP or want others to know how your company can contribute to such a proposal, we invite you to log your information at pembina.org/reframed. You know, great designs require great teams, and they'll be made up of experts from multiple fields, including some of the ones listed here, the architects, the contractors. You know, you could hear Jay saying, get us in early, we can get partners in to get you the right equipment. So the information that you submit to our portal will be published online, and that's really to help industry to discover you know, new opportunities and new innovations that maybe they didn't know about before. We're particularly interested in seeing if there are solutions that can be more prefabricated, such as the one that's being done in Sundance. As we talked about today, we were looking for high efficiency, low carbon mechanical systems, roofing solutions that integrate on-site renewable electricity, storage or renewable thermal generation, seismic upgrades, climate adaptation measures, and system controls and performance modeling, and all of these things, thinking about them in a more integrated way so that we're not piecemealing this and we can actually find some cost efficiencies. We really want to hear about your thoughts on retrofitting heat pumps, so please fill out the survey that should arrive in your inbox as soon as this session ends. We really hope that you enjoyed this webinar, and we look forward to connecting with you and all of your friends working on climate resilience at our next webinar, June 10th. Please sign up for climate resilience and deep retrofits at pembina.org/reframed tech series, which will be hosted by my colleague Gazelle Ibrahimi, who is helping us with the Q&A today. If you have any further questions about Reframed or any interested in learning how your company can get involved, you can visit pembina.org/reframed to sign up for updates and register your solutions. So thanks, folks, for all your contributions.
No
Thank you.
Thank you, everyone.
Great day.